Hi, hi everyone. Thank you very much. I'm super happy to be here in Dubai and talk about something that I feel is very important, which is simplicity. I think this is something that we don't talk about enough. So I propose that we just start by maybe saying what simplicity is. So I just copy-pasted the definition from the Cambridge Dictionary. So what's simplicity? Well, it's the fact that something is easy to understand or do. So now you might actually ask yourself the question, why the heck this talk? So simplicity is actually critical for building robust systems. That's something we've known for a long time. And I feel that sometimes there is a misconception that cutting-edge engineering is incompatible with simplicity. And actually, that's quite the opposite, I feel. So the beauty of software engineering is actually to solve complex problems with simple solutions, not the opposite. You don't believe me? Well, maybe you actually believe this guy, which said that simplicity is the ultimate sophistication. I think that's really true. So now, why simplicity in blockchain engineering? Well, simplifying means decreasing engineering time, decreasing costs, decreasing cognitive loads, both for developers and people that are going to review your code, and thus decreasing the likelihood of bug and increasing security, which is, of course, extremely important in blockchain protocols. As Einstein said, keep it simple as possible, but not simpler. So if you had to just remember one sentence from this talk, it would be stop over engineering. That's it. But I guess we have to extend a bit. So let's see where does complexity come from. Well, there I just put a bunch of ideas. It's definitely not extensive, that I grouped in a bunch of categories. So it can come from the mindset, so the way you approach your protocol, right? The design, of course, the development practices, and then external factors, such as like interaction with like other systems. Something really interesting that we observe in pretty much all software that have been developed is that the complexity naturally increases over time. So we really have to tackle this problem early. If you look at, so here I just plotted like the number of lines of code in Sol-C, so the Solidity compiler. And I think we can clearly see that like it follows an exponential trend. So actually, it goes in line with like the fact that as software age, they tend to be more complex. There are like several types of complexity. So there is actually essential complexity, which is the complexity that you can't avoid, because this is what actually brings value to your customer and your products. But at the same time, there is also other type of complexity that is detrimental to your product. And this is the complexity that we want to avoid. So you have like accidental complexity and incidental complexity. And those kind of complexity actually arise from your design decisions. And this is what we want to drastically reduce. Something interesting that, of course, complexity is observed throughout the whole engineering chain, so from design to execution. And we should try to tackle it at basically every stage. I would like to particularly focus on UX because as an engineer myself, I know that sometimes UX is really something we actually overlook. But the truth is that when you're actually building customer-facing products, UX is extremely important. So, for instance, I've been lately reviewing some wallets, and it turns out that like, if you're building a wallet, but your customers don't have access to all the information that they need, for instance, when they're signing a transaction, it's a clear red flag. And this is oftentimes a UX problem. So, be mindful of your UX. And complexity is a bad loop. Because why? Because when it increases, it's harder to write good specs. it becomes harder to write good documentation. Same for the codes. Oftentimes it comes with like more interactions, more dependencies, and then the complexity increases even more. So we really have to tackle it early to break the loop. Now, if we want to optimize something, we have to have like KPIs, right? Like metrics to quantify it. It turns out that like it's quite hard to quantify complexity. So we have a bunch of objective metrics that we can use. So number of lines of code, or like the cyclomatic code complexity, which is something that's often used in the software industry. So it's like the number of linearly independent paths in your program. But there are also subjective metrics, and I feel these subjective metrics are often like even more important. So basically, if you are building something but you can't explain the design easily to someone else, and it actually happened to me, so I know, it probably means that like your design is not simple enough or you don't fully understand it. So how to simplify? Well, again, there are a bunch of points, but I would like to focus on 2 points mainly because I think they are the basis of everything. The first one being focus on what's relevant. That's extremely important. The second one being make simplifying your code a priority within the team. If you don't do that, you're going to end up with a complex product. So a big principle is you aren't going to need it. I feel this one is very important. So don't write code that you don't need. Actually, it sounds very simple, but when I'm reviewing code, I very frequently actually reviewing and reading code that's not even like needed in the protocol, meaning either it could be completely avoided or just like simplified by a lot. And that might be the first and most important principle. A second one is like write code that's easy to change and more importantly based on what you know now, because no one can predict the future. Otherwise, we would all be rich and we wouldn't work anymore. So write code based on what you need and you know now. Last, overthink, that's good, but don't over-engineer. Meaning, don't write code that is too generic. Just write codes that's generic enough for what you need right now, and maybe later you'll tweak it if you need. I like this statement from a guy, which is John Gall, and it's funny enough a doctor that focused for many years on system design and resilient design. And basically, this statement summarizes the fact that like all the complex systems that work properly have actually evolved from simple systems. So you can't build, if you start building a complex system from scratch, it will probably fail at some point. So, simplicity requires design, because people do not naturally build simple systems. We actually like complexity as humans. So what's a good design? Well, it's something that you can easily explain, something that you can draw and write about. If you can't draw your design, it probably means it's not that simple. It's something that do not always reinvent the wheel, but only when needed. And it's something, more importantly, that's driven by global decisions, not local decisions. So here, this is something that the NASA wrote. So they did an amazing study about flight software complexity, because of course this is mission critical. And that's what they say, engineers and scientists often don't realize the downstream complexity entailed by their local decisions. Meaning that like, you really have to think about the design and work with all the team if you want to end up with like a simple product. It's not that engineers want to build a complex product. It's just that like, they're all working on their own components and just don't realize the overall complexity that like they're building together. So I guess if you can answer that question, it probably means that like you're on the right track. If you can explain to a 5-year-old children your design, it probably means it's already like quite nice from a simplicity perspective. So I just wanted to illustrate this talk with like a quick example of a not so great design. So I don't know if you know that product, but this is one of the biggest failure of like Silicon Valley. So this startup called Juicero raised like hundreds of millions of dollars to build a juicer. And it turns out that they ended up with this machine that's supposed to take a bag of veggies and just press it to make juice. It turns out that like people realized that instead of buying this $400 machine, they could just take the bag and press it with their own hand, and they would end up with the same juice. So, yeah, design is all about trade-offs. No requirements is really bad, because then you don't have a good design. But too many requirements is also bad, because you might end up with like a product that's too complex. So you have to find this thin line between the two. So here's an example, right? So if I write this requirement, an easy-to-clean device that efficiently extracts juice with minimal efforts, I might, as an engineer, end up with this. But now, assume I write that. I'm not going to read it because it's too long. But I end up with this, and it's a useless product. So now, what's a good design? Well, you can illustrate that with like a sticky note, for instance. This is a good product, very simple, solves a problem, helps me to remember important stuff, and it does it right. Maybe something that you're more used to, Uniswap. I think it's a good example of a great DeFi protocol. Very simple code, few contracts, clear separation between them, great documentation, just great example, yeah. If you're building a DeFi, you should take inspiration. So write, draw, put your design on a sheet of paper, and if you cannot do it, it's probably too complex, and you can simplify. Something also really important, make sure that you perfectly, and I want to stress the perfectly, understand all the system that you interact with, otherwise you might end up in a bad loop. It's also better to safeguard than to assume, meaning that like when you interact with external systems, you should implement as many preventive measures as needed, because if an external system is compromised, you want to avoid the repercussions on your own system. And lastly, simplicity requires thinking. So there's an example, right? Finding duplicates in a sorted array. So I think this is a funny example. On the right, you have like the naive solution, just two nested for loops, order n squared complexity. And on the left, you have like a much more elegant and simple solution, which uses the natural ordering of addresses. So sometimes, let's say, the most simple solution can require a bit of creativity. I like this guy, and I think he stated like pretty much everything. So yeah, simple can be harder than complex, and you have to work to end up with like the simple solution. Make your code readable. That's of course extremely important because at some point some people are going to review your code, and we are all humans. So to do a great work, we have to exactly understand what you want to express, and it's much easier to review code that's readable. So be consistent, follow conventions. If you're doing something in one place, do it in every place. Follow the standards. It makes your code a lot more secure. This is a bad example. I don't know if you know the USDT contract, but basically their approve function is not ERC20 compliant. And a lot of devs have to actually circumvent that, and that's annoying. Write good documentation. I know no one likes to write documentation, but it is extremely, extremely important. Write comments, but good comments. Explain why you did something, not what the code is doing, what the code is doing. Everyone can infer it. Just read the code, why it's much harder. Finally, of course. We also don't like that as devs, but test your code. Unless you've tried it, you don't know that it works. And use all the tools at your disposal, meaning fuzzing engine, unit tests, symbolic execution if you want. Yeah, all the bells and whistles. And finally, if you're a cool security researcher and want to work in an amazing team of incredible security researchers, just feel free to ping me. And it will be a pleasure to connect. Thank you very much.
All right. Thank you so much.